Three ancient civilizations discovered the same mathematical secrets. The Maya, the Egyptians, and the Mesopotamians, divided by immense oceans and centuries, all unlocked a hidden numerical code governing the heavens and the earth. In this journey, you will see how their separate paths led to an identical understanding of time, space, and architecture, revealing a universal human genius. How could builders of pyramids on opposite sides of the world use the same sacred geometry? Why did astronomers who never met calculate the year with near identical precision? The answers will reshape everything you thought you knew about our ancient past. What does it say about us that the same numbers speak across the ages? A wedge pressed into damp clay, a simple mark that would echo for millennia. In the hands of a Mesopotamian scribe, this was more than record-keeping. It was the birth of a revolutionary idea. They devised a system where the value of a symbol changed depending on its position. A single wedge could mean 1 or 60 or 3600. This concept of place value, which we use effortlessly today, was a monumental leap in human thought. Far across the world, the Maya were building a numerical universe of their own, rooted in the number 20. Their system used just 3 symbols, a dot for 1, a bar for 5, and a stunningly advanced concept, a shell to represent nothing, a true 0. This allowed them to write immense numbers and perform calculations of breathtaking complexity. Meanwhile, along the Nile, Egyptian administrators used a base 10 system, inscribing hieroglyphs that represented units, tens, and hundreds. A single stroke was 1, an arch was 10, a coiled rope 100. With these symbols, they calculated the wages for laborers and the precise angles for their monumental pyramids. On the surface, these 3 systems appear completely different, one carved in stone, another written in codices, the third impressed in clay. Yet they were all engineered to solve the same fundamental problems. They needed to count grain stores, to track the passing seasons, to chart the wanderings of planets. This was not abstract number theory. It was mathematics forged in the fires of necessity. Each civilization, working in total isolation, felt the same compelling need to impose a numerical order upon the chaos of the world. This shared foundation in practical calculation, this universal language of quantity, would soon allow them to hear the same rhythmic patterns in the silent music of the stars. That shell symbol for 0 was not just an empty space, it was a conceptual thunderclap. It meant nothing could be something, a placeholder that gave structure to the infinite. With it, a Mayan priest could chart the cosmos, calculating lunar cycles that stretched for thousands of years into the future. At the very same time, though separated by a vast continent and an ocean, a Babylonian astronomer was making his own celestial predictions. His tool was a different framework, a base 60 system etched into a clay tablet. He grouped numbers in 60s, a method so enduring it still dictates how we measure our hours and minutes today. On the surface, a base 20 system and a base 60 system seem worlds apart. Why would one culture count on their fingers and toes while another settled on 60? Yet the underlying principle they both discovered is what truly matters. It is the revolutionary idea of place value. In both systems, the exact same symbol, a dot or a wedge, could have a completely different meaning. Its value was not inherent but was defined by its position. A single dot in the first position was 1. That same dot moved to the second position, suddenly represented 20 for the Maya or 60 for the Babylonian. This was the genius leap. It was no longer just counting objects, it was manipulating an abstract framework, a logical grid that could scale to infinity. This was the birth of true computational power. Imagine the intellectual spark that had to ignite independently in these two brilliant, isolated minds. They were not copying one another. They were both tapping into the same fundamental pathway of human logic, a convergent evolution of thought. They built different vehicles, but they were navigating the same mathematical landscape. And this powerful new tool, this ability to handle immense numbers with elegant simplicity, was absolutely essential. They were about to turn their gaze upward, to face their next and greatest challenge, to map the seemingly chaotic dance of the heavens themselves. The heavens presented an endless puzzle, a grand clockwork of moving lights. To solve it, these ancient astronomers became masters of patience, watching the sky for generations. In the jungles of the Maya, this vigil produced a number of stunning accuracy. They calculated the solar year as 365.2420 days. This is almost identical to our modern measurement. They achieved this not with telescopes, but with precise alignments in their stone observatories, tracking the sun's slow journey north and south. Along the Nile, the Egyptians developed a simpler but brilliantly practical 365-day civil calendar. It guided the rhythm of their agriculture, predicting the Nile's life-giving floods. And in the dusty plains of Mesopotamia, scribes perfected the prediction of eclipses. They discovered the Saros cycle, a pattern of approximately 18 years after which the sun, moon, and earth returned to the same relative positions. Think of the intellectual courage this required. A scholar would begin recording an eclipse, knowing he would never live to see the full pattern revealed. He was gathering data for his grandchildren's grandchildren, a legacy of observation etched in clay. The mathematical tool they all used was the progression, a sequence of numbers that grows by a constant rule. It is the heartbeat of a calendar. You add a certain number each day, each month, each year, and eventually the pattern repeats, revealing the hidden order within the celestial dance. This was not merely an academic exercise. This knowledge of time was power, and it was sacred. It told them when to plant, when to celebrate, and when the gods might be appeased. And so they built their faith not just on prayer, but on the unshakable certainty of mathematics. They translated these celestial cycles into something permanent and awe-inspiring, into monuments of stone that reached for the very stars they studied. Stone and sky met with an intention so precise it defies simple explanation. The Great Pyramid of Giza was not merely built, it was oriented. Its sides aligned to the four cardinal directions with an error of less than 1/15 of a degree. This was an act of geometric mastery repeated across the world. In Mesopotamia, the massive ziggurats rose like stairways to the gods, their squared bases and ascending levels a testament to a shared understanding of form. And in the Maya world, temples pierced the jungle canopy, their proportions echoing a sacred mathematics. These were not just buildings, they were three-dimensional prayers, physical equations meant to harmonize the human world with the cosmos. The principles governing their construction reveal a universal architectural language. The Egyptians, for instance, frequently employed a specific ratio known today as the golden ratio, a proportion of approximately 1.618 to 1, which appears in the dimensions of their tombs and their art. It is a relationship found in the growth patterns of shells and the branching of trees, a ratio perceived as the very signature of natural beauty and divine order. Meanwhile, researchers have found that the layouts of certain Mayan structures seem to incorporate Pythagorean triples, sets of three whole numbers that perfectly satisfy the famous theorem for a right-angled triangle, a full millennium before Pythagoras himself was born. Why would these specific shapes and numbers appear again and again? The answer lies in a profound belief that the universe itself was built upon a framework of perfect geometry. By recreating these perfect forms on Earth in stone and mortar, these civilizations believed they could tap into a cosmic power, creating a sacred space where heaven and earth met. This shared vision required more than just philosophical insight. It demanded tools of incredible accuracy to translate abstract ratios into mountains of stone. An architect along the Nile held a rod of polished wood, the royal cubit, its length defined by the distance from a man's elbow to the tip of his middle finger. With this single, standardized unit, repeated thousands of times, he could direct the construction of a pyramid that would stand for millennia. Far to the east, a Mesopotamian surveyor stretched a rope knotted at precise intervals, his reed measure ensuring every wall in a new temple was straight and true. Their tools were different, but their goal was identical: to impose a consistent mathematical order upon the physical world. This was the birth of measurement as a universal language. The Egyptian cubit was rooted in the human form, a personal scale made official. In Mesopotamia, units were often tied to the rhythms of agriculture. A shekel was a specific weight of grain. A measure of volume was defined by the capacity of a common jar. This drive for standardization was not born from abstract science, but from the relentless demands of reality. How do you pay a workforce of thousands if the meaning of a day's ration changes from one town to the next? How do you tax goods arriving from distant lands without a common understanding of volume and weight? The answer was a system of measurement so reliable it became the bedrock of law and commerce. This practical application of mathematics organized society itself. It allowed for the planning of cities with straight avenues and canals that fed entire regions. It enabled trade networks to stretch across continents, because a merchant in one kingdom could trust the measure of cloth or grain promised by a partner in another. The vast urban landscapes of the ancient world, with their monumental architecture and complex economies, were not just feats of engineering. They were testaments to a shared human instinct to quantify, to compare, and to build upon a foundation of agreed-upon truth. This web of trade did more than move goods. It began to weave these separate mathematical worlds into a single, interconnected tapestry of ideas. The concept of nothingness is one of humanity's most profound and daring intellectual leaps. To look at an empty space and declare it a number required a radical shift in perception. The Maya embraced this abstraction fully, carving a shell glyph to signify zero in their long count calendar over 2,000 years ago. It was not merely an empty space on a stone tablet. It was an active participant in their calculations, a placeholder that gave structure to immense spans of time. In the administrative centers of Mesopotamia, a similar need arose. Scribes, meticulously recording quantities of grain or parcels of land, would leave a careful gap in their cuneiform columns to indicate an empty order of magnitude. This was a placeholder, a silent acknowledgement of an absence that still held mathematical power. The Egyptian system, by contrast, did not develop a distinct symbol for this concept, yet their complex accounting demanded ways to represent missing values. This parallel grappling with the void, from the jungles of Central America to the river valleys of the Middle East, points to a fascinating inevitability. As civilizations grew more complex, as their mathematics strained to handle larger numbers and more abstract problems, the invention of a symbol for nothing became not just useful but essential. It was an idea whose time had come. This intellectual tool transformed administration. Imagine a Maya official calculating the tribute owed from a distant province. With a positional system and a zero, he could efficiently manage sums that would have been a tangled mess in a simpler notation. In Mesopotamia, that carefully placed gap in a ledger allowed for accurate records of harvests and distributions, the very foundation of their urban economy. The leap to conceptualize nothing was paradoxically what enabled everything. It unlocked the potential for the higher mathematics that would chart the stars and raise timeless monuments. The records they left behind, etched in stone and clay, offer us a direct window into how this powerful idea began to reshape their world. A river of commerce flowed through the ancient world, and mathematics was its current. On a Mesopotamian dock, a scribe's stylus moved quickly across a damp clay tablet. He was calculating the tariff on a shipment of copper, using established rates to multiply the weight by the duty owed. This exact same scene, with different tools but identical principles, unfolded in the granaries of Egypt. Scribes there used hieratic script on papyrus to meticulously account for every sack of grain, its volume measured for both taxation and redistribution to the workers building a pharaoh's tomb. Far across the sea, a Mayan administrator recorded the tribute owed by a subject city, his bark paper codex filled with bars and dots that tallied jade, feathers, and cacao beans. These were not isolated acts of bookkeeping. They were the vital signs of a complex society, a proof that numeracy was the essential backbone of civilization itself. The mathematics required was sophisticated. Loan agreements found on cuneiform tablets detail compound interest growing over time. Egyptian administrative papyri show the calculation of land areas for taxing farmers, using geometric formulas to account for irregular plots beside the Nile. This was not abstract theory. It was the practical, relentless arithmetic of survival and growth. Every measurement of a field, every calculation of a worker's grain wage, every tally of stored oil relied on standardized units and repeatable procedures. This administrative efficiency created something extraordinary, a surplus. By managing resources with mathematical precision, these cultures generated the excess wealth needed to support not just laborers but the thinkers. The scribes, the astronomers, the architects, they all stood upon the foundation of this economic engine. The precise calendars that tracked the years and the soaring pyramids that defied them were ultimately funded by the humble, relentless calculation of a tax on goods. This intricate system of numbers, born from the need to count and trade, would soon face its greatest challenge not in the marketplace, but in the silent, infinite expanse of the night sky. A circle presents a perfect puzzle, a shape with no beginning and no end. How do you measure its curve or calculate the space inside it? This was not a question for idle philosophers, but a pressing concern for the builders and astronomers of the ancient world. In Egypt, a scribe unrolled a papyrus scroll, known today as the Rhind mathematical papyrus. His problem was practical, to determine the area of a circular grain silo. His solution was a brilliant shortcut, instructing the reader to take the diameter, remove 1/9 of its length, and then square the result. This method, when translated into our modern terms, uses a value for pi of approximately 3.1605, a remarkably close approximation for its time. A world away, a Babylonian administrator working on a clay tablet might use a simpler rule, squaring the circumference and dividing by 12, which relies on a pi value of exactly 3. These were not the infinite, irrational constant we learn in school, but they were powerful, working numbers that got the job done. The evidence for the Maya is etched in stone rather than written in explicit formulas. Their obsession was not with static circles, but with celestial cycles, the great circular motion of time itself. The precision of their calendar, a complex interlocking of cycles, suggests a mind comfortable with the mathematics of rotation and periodicity. Why did these cultures, in isolation, all converge on similar solutions? They were driven by the same inescapable needs: A well must be dug to a specific circumference to support its walls. A grain storage pit must hold a known volume of harvest. The circular path of a planet had to be understood to predict its return. Their methods were empirical, born from trial and observation, from measuring ropes and comparing results. They found a number that worked for their world, a practical key to a geometric lock. This shared ingenuity, this independent push to solve the circle, reveals a deeper truth. The human mind, when faced with the perfection of nature, will always strive to find the number hidden within the shape. A heap, its quantity unknown, combined with its seventh part makes 19. This was the puzzle an Egyptian scribe pondered nearly 4,000 years ago, recorded in the Ahmose papyrus. He was not merely doing math, he was hunting for a hidden number, a process we now call algebra. His method was elegant, assigning a false value to the heap to untangle the relationship, then scaling the answer to find the truth. This was not an abstract exercise. It was the mathematics of daily survival, used to divide bread among workers or to calculate the right amount of land for an inheritance, ensuring a family's legacy was fairly split. Across the sands of time in Mesopotamia, a different scribe faced a similar challenge. His clay tablet presents a problem we would recognize as a quadratic equation. He describes a field, its area, and the relationship between its length and width, and he provides a step-by-step procedure to find the dimensions. He did not use a symbolic formula with x and y. Instead, he followed a set of verbal instructions, a geometric algorithm that effectively completed a square to reveal the answer. These were not isolated sparks of genius, but a widespread mode of thought. These civilizations were constantly manipulating relationships between the known and the unknown. They understood that quantities could be linked, and that if you could define the relationship, you could solve for what was missing. This was a monumental leap from simple arithmetic, where one merely adds or subtracts fixed amounts. This was relational thinking, the true heart of algebra long before it had a name. It was a logical framework built not in a vacuum, but one that mirrored their view of the cosmos, a universe where everything was interconnected, where hidden patterns and balanced relationships governed everything from the movement of planets to the fair distribution of grain. This powerful tool for managing the physical world would inevitably lead them to confront the ultimate abstraction, the profound and unsettling concept of infinity itself. Numbers whispered secrets of the gods. For the Egyptians, the number 4 was not just a quantity, it was a sacred protector, embodied by the 4 sons of Horus who guarded the canopic jars containing the vital organs of the departed. This was a divine quartet, a numerical anchor in their spiritual universe. In Mesopotamia, a scribe might examine the pattern of cracks on a heated sheep's liver, searching for a numerical omen that could foretell the fate of a king or the success of a harvest. Every pattern held a potential message from the gods, a code to be deciphered, and in the Mayan world, the numbers 13 and 20 formed the very scaffolding of existence. Their sacred calendar was a complex interlocking of a 13-day cycle and a 20-day cycle, creating a 260-day ritual year that governed ceremonies and divination. This was more than counting, it was conversing with the cosmos. To see the world this way is to understand that for these cultures, mathematics was a two-edged sword. One edge was practical, cutting straight to the solution of an engineering problem or a market calculation. The other edge was mystical, cutting through the veil to reveal a hidden, divinely ordered reality. The rhythmic cycles of the planets, the perfect angles of a pyramid, the balanced proportions of a temple, these were all expressions of a celestial harmony written in the universal language of number. This profound belief that the universe was fundamentally mathematical provided an immense spiritual motivation for their intellectual pursuits. A priest astronomer would spend his life calculating the orbit of Venus not just to predict its movement, but to understand the mood of a god. An architect would perfect the proportions of a tomb not merely for stability, but to ensure the soul's safe passage into a numerically perfect afterlife. The legacy of this sacred quest is not just in the grand monuments, but in the fragile pages of surviving texts and the intricate carvings on artifacts, where the cold logic of calculation is forever entwined with a warm, human yearning to find meaning in the patterns of creation. A fragile sheet of bark paper covered in intricate bars and dots held the mathematical wisdom of a Mayan priest. Most of these codices, however, did not survive the humid jungle climate and the destructive fires of conquest. Their knowledge vanished into smoke and decay. In stark contrast, a Mesopotamian scribe's account of a loan with compound interest was pressed into a wet clay tablet, hardened in a kiln or even preserved by the very fire that destroyed a city. These are the fragile vessels that carried the mathematical genius of the ancients across millennia. The Egyptian Rhind papyrus, a scroll over 15 feet long, is not a simple list of answers. It is a textbook, a master scribe instructing his student. Each problem is presented, then followed by a careful, step-by-step explanation of the procedure, a voice from the past teaching us how to think. The Babylonian tablet known as Plimpton 322 is even more astonishing. It is not a narrative but a table, a structured list of numbers that modern researchers believe was used for advanced calculations, perhaps for determining the dimensions of right-angled triangles or for complex engineering projects. This is the raw data of their intellect. Piecing this legacy together is a monumental task of modern scholarship. Epigraphers spend years, sometimes decades, staring at damaged surfaces, painstakingly matching fragmented symbols to reconstruct a single sentence. They are not just translating words, they are decoding a mindset. Before we can truly compare the pyramids of Egypt to the temples of the Maya, we must first understand the foundation upon which our knowledge is built. A foundation made of cracked clay, frayed papyrus, and the patient, relentless work of those who listen for whispers in the dust. The cracked clay of a Mesopotamian tablet holds columns of numbers so precise they could calculate the square root of 2. This was a civilization that turned mathematics into a powerful computational engine, their algebraic tables revealing a mind obsessed with numerical relationships. Along the Nile, the Egyptian approach was sculpted by the river itself. Their geometry was not abstract but profoundly practical, born from the annual need to resurvey farmlands after the floodwaters receded and to calculate the exact slopes of their pyramids. Their mathematical genius was one of measurement and mastery over the physical world, and high in the jungle, the Maya gazed into the deep well of time. Their mathematical system, with its elegant positional notation and explicit zero, was a vehicle for navigating vast cosmic cycles, for seeing patterns that stretched across centuries. So which was the most advanced? The question itself is a trap. Sophistication cannot be measured on a single scale. It is a reflection of purpose. The Mesopotamians built an empire of calculation, the Egyptians an empire of stone, and the Maya an empire of time. Each civilization honed its mathematical toolkit to solve the unique puzzles presented by its environment, its gods, and its society. This was not a race toward a single finish line. It was a brilliant, global flowering of the human intellect, a branching tree of discovery where every branch found its own sun. This stunning parallel evolution forces us to confront a mystery that has haunted historians for generations. Could a whisper of an idea have crossed an ocean, or did the same pattern simply emerge from the very structure of the human mind? this question cuts to the very heart of human history. Did a single lost thread of knowledge connect the Maya, Egypt, and Mesopotamia, or did they each weave the same pattern from scratch? The diffusionist argument suggests a whisper of an idea could have traveled across uncharted seas. Perhaps a lone vessel blown off course carried a new way of counting, maybe trade routes longer and more interconnected than we ever realized, served as a slow-motion relay for fundamental concepts. The evidence for this, however, remains tantalizingly circumstantial, a ghost in the historical record. The opposing view, that of independent invention, presents a powerful counterpoint. It argues that when any human society reaches a certain level of complexity, certain discoveries become almost inevitable. The need to manage large harvests will push you toward advanced arithmetic. The drive to build monumental structures demands reliable geometry. The obsession with understanding the gods in the sky forces you to invent precise astronomy. Similar problems faced by intelligent minds will often yield similar solutions. This is the principle of convergent evolution in the realm of ideas. Think of it like this: if you give two isolated groups the same puzzle with the same set of logical pieces, is it so surprising if they both eventually find the same way to fit them together? The human brain, with its capacity for pattern recognition and abstract thought, is the ultimate puzzle-solving machine. The true mystery, then, may not be the contact between these cultures, but the shared architecture of the human mind itself. The numbers they discovered were not invented so much as they were unearthed, waiting like buried diamonds for anyone with the intellectual tools to dig. The brain of a Mesopotamian priest tracing Venus and the mind of a Mayan astronomer calculating a lunar cycle were running on the same fundamental hardware. Cognitive scientists point to a universal human capacity, an innate number sense that allows even infants to instantly recognize the difference between one object and three. This biological foundation, this shared cognitive starting point, is the deep root from which all mathematics eventually grew. It is our common ability to subitize, to instantly grasp small quantities without counting, and to estimate larger amounts that provided the raw material for every numerical system that followed. This number sense was then amplified and refined by the unique pressures of each culture. The need to administer a city along the Nile demanded a formal system of numerals. The drive to predict celestial events in the Yucatan required a sophisticated calendar. Language gave these abstract quantities names, and symbols gave them a permanent form, transforming an intuitive gut feeling about more and less into a powerful, shareable tool. The independent discovery of concepts like place value and geometric ratios may not be a historical coincidence, but a cognitive inevitability. They represent universal stages in the evolution of complex thought, logical steps that any advanced society would likely discover once its collective mind began building upon that innate numerical foundation. This reveals a stunning truth that mathematics is not merely a human invention, but a landscape of discovery whose contours are shaped by the very structure of our minds. Our shared neural wiring provided the engine, the common cognitive toolkit that transformed raw astronomical data into a predictive science, allowing these separated cultures to independently decode the same cosmic rhythms. A single cuneiform wedge marking the position of Jupiter on a specific night was just one data point among thousands. But when a Mesopotamian astronomer laid out the tablets of his predecessors, spanning decades of meticulous observation, a rhythm began to emerge from the noise. He saw that the planet's looped path across the sky repeated itself, not randomly, but in a grand, predictable cycle. This was the moment of profound discovery, the leap from simply recording events to foreseeing them. It was the power of pattern recognition, the human mind imposing order on celestial chaos. The Maya performed this same intellectual feat with the planet Venus, calculating its 584-day cycle with such precision that their predictions were accurate for centuries. Along the Nile, Egyptian priests transformed the Nile's unpredictable flood into a forecastable event by correlating its arrival with the heliacal rising of the star Sirius. Their method was iterative and brilliantly practical. They would compare cycles looking for the lowest common multiple, the point where shorter rhythms align to create a longer, more stable calendar. This empirical, data-driven approach is the bedrock of the modern scientific method, and its deep roots in these ancient cultures reveal a universal human talent for inductive reasoning. We see the same pattern and build a model for what comes next, but these celestial models were far more than academic exercises. The ability to predict an eclipse or the flooding of a river was a form of power so immense it shaped the very structure of society. A king who could announce the gods' intentions, as read in the stars, solidified his divine right to rule. A priestly class that held the calendar held the keys to all agricultural and religious life. This knowledge was the original state secret, a tool of governance and social control. The true legacy of these ancient scientists is not just in the accuracy of their predictions, but in their foundational belief that the universe is, at its heart, a comprehensible system of repeating patterns, waiting for a patient and observant mind to decode its secrets. The authority to predict an eclipse was a form of magic made real. This was not a secret kept in dusty libraries, but a public demonstration of power that could silence a city. When a priest astronomer foretold the moon swallowing the sun, he was not just proving his calculations' accuracy, he was proving his direct line to the gods. That knowledge was a political weapon, legitimizing the king who sponsored him and the entire social order they upheld. In Egypt, this control was woven into the very fabric of life along the Nile. The state's scribes did not merely record the annual flood, they used generations of data to model its arrival. By announcing the coming inundation, the pharaoh positioned himself as the guarantor of the harvest, the divine intermediary upon whom all life depended. This precise prediction was the foundation of the entire economy, dictating when to plant, how much to tax, and how to distribute the grain that fed thousands of laborers building monuments to the state's own glory. In Mesopotamia, the power of the scribe was equally immense. The sprawling empires of the region ran on a river of information recorded on countless clay tablets. These were not just lists, but complex administrative records detailing everything from military supplies to land ownership to the rations for a workforce of thousands. Mathematical literacy was the key that unlocked this bureaucratic machine. A scribe who could calculate interest on a loan, manage the logistics of a distant garrison, or survey a field for taxation was not a mere accountant. He was a central cog in the empire's engine of control. This state sponsorship fundamentally shaped the development of mathematics itself. Knowledge was no longer just a collection of clever tricks. It became a formalized curriculum, a body of standardized problems and solutions taught in scribble schools to produce new generations of administrators. The student who mastered these tablets was not just learning math, he was learning how to uphold the power structure, to quantify, to regulate, and to command. The equations they solved were the blueprints for civilization itself. A young boy in Mesopotamia sat for hours, his hands cramping as he pressed wedge after wedge into a damp clay tablet. This was the Adaba, the tablet house, the training ground for the civilization's administrative elite. His education was a relentless drill of memorization, copying endless lists of multiplication tables and standard mathematical problems. The same scene with different tools unfolded along the Nile. An Egyptian scribble student practiced his hieratic script on a flake of limestone, repeatedly solving problems of distributing loaves of bread or calculating the area of a field. His textbook was a papyrus scroll filled with model solutions, a master's work to be copied until the procedure became second nature. While the ruins of formal Mayan schools are less clear, the sheer complexity of their calendar and glyphs tells its own story. Mastering the intricate long count and the interlocking cycles of time required years of dedicated instruction, likely within the quiet chambers of temple complexes under the guidance of priestly scholars. This was not education for its own sake. It was the rigorous, formalized transmission of a vital technology. By standardizing the curriculum, these cultures created a professional intellectual class, a continuity of knowledge that spanned centuries. The mathematical techniques used by a grandfather to survey a field would be identical to those used by his grandson, refined only through accumulated experience. The survival of student tablets, complete with a teacher's corrections scratched in the margin, gives us a priceless gift. It allows us to see not just the final, polished achievements, but the messy, human process of learning. We hear the echo of a master's voice guiding a novice through a difficult calculation, a chain of instruction unbroken for generations. This system of formal education was the engine that powered their intellectual ascent, ensuring that each new mind did not have to rediscover the wheel, but could stand on the shoulders of giants and reach just that much higher. Yet even the most brilliant minds are bound by the horizons of their time. The Egyptian formula for a truncated pyramid's volume was a stroke of genius, a practical solution for a specific shape, but it was not a generalized theorem that could be applied to any solid. Their value for pi 3.1605 was an elegant approximation that worked perfectly for building granaries and calculating grain, yet it was not the infinite, irrational constant we know today. This was a mathematics rooted in the tangible world, a collection of powerful techniques rather than a system of abstract proofs. The Greek tradition, which would later emerge, sought universal truths through deductive logic and axiomatic foundations. The Egyptian and Mesopotamian approach was different. It was brilliantly empirical, built case by case to solve the problems right in front of them. Their cultural priorities created both extraordinary focus and inherent boundaries. The Mayan obsession with cyclic time, for instance, led them to create a calendar of breathtaking complexity, a masterpiece of long-term astronomical observation. Yet this very focus on celestial cycles may have limited their exploration of other mathematical avenues, such as the more abstract geometry of shapes. Acknowledging these limitations does not diminish their achievements. In fact, it makes them far more remarkable. They were not superhuman beings gifted with perfect knowledge. They were ingenious problem solvers who built towering intellectual edifices with the tools and materials they had available. They worked within the constraints of their worldviews, pushing the boundaries of the possible as far as their cultural context would allow. Understanding where their knowledge ended is just as important as understanding where it began, for it frames the true scale of their legacy and sets the stage for the fragile journey this knowledge would take across the centuries. Great centers of learning fell silent. The bustling scribble schools of Mesopotamia were buried under the dust of fallen empires, their libraries of clay tablets shattered and scattered. The intricate calendar rituals of the Maya faded as their city-states were gradually reclaimed by the jungle, the precise knowledge of the priest astronomers dissolving into fragmented memory. In Egypt, a long twilight of foreign rule slowly transformed the old ways, and the direct line of pharaonic mathematical tradition was eventually broken. These were not mere changes of government. They were systemic collapses that severed the chain of oral and scribble instruction, causing entire libraries of sophisticated thought to vanish almost overnight. The most profound loss was the Maya's elegant positional system, complete with its explicit zero. This conceptual leap, so vital for high-level calculation, simply disappeared from use in the region, a brilliant light extinguished. Similarly, the full context and underlying reasoning for many advanced Mesopotamian algebraic techniques were buried, leaving behind only the answers on cracked tablets without the master's voice to explain the journey. Yet the story does not end in total darkness. A resilient thread of their genius was woven into the fabric of our daily lives. Every time you check the clock, you are counting in the Babylonian manner. Their base 60 system, chosen for its mathematical elegance, still defines our 60 minutes in an hour and 60 seconds in a minute, a direct inheritance from their astronomical tables. The practical geometry of the Egyptians, their methods for measuring land and volume, was absorbed by the Greeks and Romans, becoming a cornerstone of classical learning and eventually our own. These are the enduring fragments, the echoes in our modern world that prove the robustness of their ideas. The river of knowledge did not dry up completely. Its course was dramatically altered, with some streams vanishing into the sand while others found new channels, flowing quietly into the future, carrying the timeless patterns discovered by the ancients. A broken piece of black basalt, pulled from the mud of the Nile Delta, became the master key to an entire civilization. The Rosetta Stone, with its parallel inscriptions in Greek and Egyptian hieroglyphs, did not simply give us the pharaohs' names, it gave us their voice. Scholars like Jean-François Champollion realized the hieroglyphs were not just pictures but a complex mix of sound and meaning, and with that realization, the mathematical and administrative papyri suddenly began to speak. They were no longer curiosities, they were textbooks. A similar intellectual feat occurred with the cryptic wedges of Mesopotamian cuneiform. Pioneers like Otto Neugebauer spent a lifetime staring at columns of numbers on clay tablets, slowly recognizing them not as random lists, but as highly sophisticated multiplication tables, reciprocal tables, and even algorithms for solving quadratic equations. They were looking at the raw computational engine of an empire. For the Maya, the decipherment was even more daunting. With most of their bark paper books lost, researchers had to correlate the dates carved on stone stelae with known astronomical events, like the position of Venus on a specific night in the 8th century. When the patterns finally aligned, it was as if a massive, intricate clock had suddenly begun to tick again, revealing a civilization that measured time with staggering precision. Each of these breakthroughs was a collaborative triumph, the work of archaeologists, linguists, and mathematicians standing on each other's shoulders. Today, this detective work continues with powerful new tools. High-resolution digital scans can detect faint impressions on a broken tablet that are invisible to the naked eye, revealing a previously unknown calculation. Data analysis programs can search for patterns across thousands of inscriptions, finding connections no single scholar could ever see. This ongoing research does more than just fill in gaps in the historical record. It fundamentally rewrites the history of science itself. It proves that the journey of human discovery is not a straight line from primitive to advanced, but a story of brilliant flashes of insight, catastrophic losses, and patient, piece-by-piece rediscovery. The true puzzle is not just what they knew, but how we managed to hear their whispers across the void. The timeline of mathematical discovery is a map we have long drawn incorrectly, with Greece as its solitary center. For centuries, the narrative held that abstract reasoning began with Thales and was perfected by Pythagoras. Yet the clay tablets of Mesopotamia and the papyri of Egypt tell a very different story. They reveal that the core principles of geometry and algebra were already ancient by the time Greek philosophers began their own inquiries. This is not to diminish the Greek contribution, which was profound in its shift toward axiomatic proof, but to place it within a far wider, older conversation. The Greeks themselves often spoke of learning from the Egyptians, of traveling to the Nile to study with priests who held knowledge spanning generations. Our modern textbooks, however, have frequently erased these debts, presenting a story of European genius blooming in isolation. The evidence demands we redraw the map entirely. We must see the ancient world as a constellation of intellectual powerhouses, each illuminating a different facet of a universal human endeavor. The Maya, with their deep time calculations, were not primitive mystics. They were theoretical astronomers of the highest order. The Mesopotamian scribes, with their sophisticated loan agreements and algebraic tables, were not mere bookkeepers. They were the architects of a computational logic that would underpin empires. Recognizing their independent achievements does more than just fill in historical gaps. It fundamentally changes our understanding of how innovation works. Progress is not a single torch passed from one culture to the next. It is a field of wildflowers, blooming separately yet simultaneously, each adapted to its own soil but part of the same beautiful global spring. This expanded view invites us to listen for echoes of this ancient genius in other, unexpected corners of the world, waiting to be recognized. While the pyramids of Egypt were rising, another great civilization was measuring the world along the Indus River. The people of the Indus Valley, contemporaries of the earliest Mesopotamian city-states, were using standardized weights in a precise decimal ratio. A small cube of chert represented 1 unit, while larger weights were multiples of 2, 4, 8, and 16 of that same unit. This was a society thinking in powers of 10, creating a uniform system of trade and measurement that stretched across a vast region. To the east, along the Yellow River, Chinese scholars of the Zhou dynasty were inscribing numbers on oracle bones and bamboo slips. They developed a base 10 positional system that used counting rods, where the placement of a rod determined its value as units, tens, hundreds, or thousands. This was a system of remarkable flexibility and power, capable of representing any number and performing complex calculations. Then, in India, a conceptual thunderclap occurred. Sometime before the Common Era, Indian mathematicians formally defined the number 0, not just as a placeholder, but as a tangible quantity in its own right. They called it sunya, meaning void or emptiness. This profound abstraction, this full embrace of nothing as something, would one day travel west and transform the mathematical landscape of the entire world. Why did these traditions, so distant from the Nile and the Euphrates, follow such similar paths? They too faced the relentless, universal demands of complex society. The Chinese state needed to calculate the volume of earth for massive public works projects, to survey land for equitable taxation, and to perfect a calendar that would legitimize the emperor's mandate of heaven. Indian astronomers, gazing at the same sky as the Maya, sought to predict planetary motions and eclipse cycles with ever greater accuracy. The solutions they crafted, from the decimal weights of the Indus to the counting rods of China, were local inventions. But the underlying impulse was global. This was not a series of isolated sparks, but a slow, steady dawning of light across the entire ancient world. Each civilization, in its own time and in its own way, was learning to listen to the same quiet, persistent rhythm, the logical heartbeat of the universe itself. A mathematical recipe tells you how to divide 19 loaves among 10 men. The solution is practical, immediate, and perfectly correct for that one specific situation. The civilizations we have explored were masters of these recipes, compiling vast collections of solved problems for every eventuality, from land surveys to celestial events. Yet a subtle but monumental shift began to occur, particularly in the bustling scribble schools of Mesopotamia. They started to develop procedures that were not just for a single problem, but for an entire class of problems. A single set of instructions etched onto a clay tablet could be used to find the dimensions of any rectangular field, provided you knew its area and the difference between its length and width. This was no longer just a recipe, it was the skeleton of an algebraic formula, a generalized tool. Simultaneously, in the Mayan world, their long count calendar was a breathtaking act of abstract thinking. It was not tied to the reign of a specific king or the lifetime of a person. It was a linear timeline stretching forward and backward from a fixed point in the mythical past, a pure, abstract count of days that could, in theory, run to infinity. This was mathematics beginning to untether itself from the immediate physical world and operate in a realm of pure ideas. They were building a framework. Yet the final, self-conscious leap to a fully axiomatic system, one built on a set of undeniable first principles from which all other truths could be logically deduced, would fall to another culture, the Greeks. Why did this happen there and then? It was not for lack of genius in the earlier cultures, but perhaps a matter of focus. The Egyptians, Mesopotamians, and Maya were, at their core, brilliant engineers and empirical scientists. Their primary goal was to get the right answer, to build the stable pyramid, to predict the reliable eclipse. The Greek innovation was to ask a different question, not just is it true, but why must it be true? They sought to prove that a statement was eternally and unchangeably correct, based solely on the power of logic. This was the birth of mathematics as we know it today. But that birth was not from nothing. The Greeks themselves stood directly on the shoulders of these earlier giants. The vast catalogue of solved problems, the identified geometric relationships, the proven techniques for calculation, this was the indispensable raw material. The Greeks did not invent geometry, they systematized it. They took the practical knowledge of the Nile surveyors and the Mesopotamian algebra and asked for the universal rules that governed them all. The journey from the specific answer to the general proof, from the practical tool to the theoretical framework, is the story of mathematics coming of age. And every great journey requires a first step, a foundation laid by those who came before. The empty space where a Mayan multiplication table should be is one of history's quietest yet most profound silences. We can see the results of their complex calculations etched in stone, the precise dates of celestial events that required immense numerical operations to predict. But the actual methods they used to multiply and divide within their base 20 system remain a tantalizing secret. Did they use a form of mental arithmetic, a lattice similar to the abacus, or tables of reciprocals like their Mesopotamian counterparts? Without a surviving instructional codex, we are left to reconstruct their thought processes from the magnificent answers they left behind. This gap in our knowledge is a constant reminder of the fragility of history. The humid jungle air that claimed most of their bark paper books may have swallowed entire libraries of theoretical work. The possibility of a single, undiscovered codex, perhaps sealed in a dry cave or buried in a yet unexcavated tomb, haunts researchers. Such a find could instantly illuminate the dark corners of Mayan mathematics, revealing not just what they knew, but precisely how they thought. Beyond the jungles, an even larger question looms. The similarities in numerical concepts across oceans are so striking that they beg for an explanation. Were these patterns carried on the currents of forgotten trade routes, a slow diffusion of ideas across millennia, or do they point to something even more fundamental, a shared architecture of the human mind that, when faced with similar problems, inevitably constructs similar solutions. The tools to answer these questions are now more powerful than ever. LiDAR technology, piercing the dense canopy of Central America, is revealing entire cities and ceremonial centers we never knew existed, each one a potential repository of new inscriptions. In museum basements, spectral imaging is being used to read the ghostly traces of ink on faded papyri and palimpsests, recovering texts that were erased and rewritten centuries ago. This is not the end of the story, but a new chapter in a very old investigation. Every shattered tablet reassembled, every jungle-covered plaza mapped, has the potential to rewrite a paragraph in the grand narrative of human discovery. The journey of these numbers across time and continent is a mirror reflecting our own relentless drive to find order in the universe. It suggests that the language of mathematics is not merely a human invention, but a native tongue of the human mind, a deep, shared current of logic that has flowed beneath the surface of our diverse cultures from the very beginning. The silent stones and faded texts have spoken. Our journey across continents and millennia reveals a stunning truth. The Maya, Egyptians, and Mesopotamians were not isolated geniuses, but part of a collective human endeavor to decode the universe through mathematics. They were separate vessels navigating the same vast ocean of stars and stone, each arriving at the same fundamental shores of understanding. They independently discovered the revolutionary power of place value, the unerring regularity of celestial cycles, and the silent harmony of sacred geometry. This was not a story of a single idea traveling the world, but of a beautiful convergence, proof that the human mind, when faced with the grand challenges of civilization, time, and the cosmos, finds remarkably similar paths to the same profound truths. Their legacy is not just in the ruins they left behind, but in the very way we structure our world, in the minutes of our hour, and the geometry of our buildings. Let this be a powerful reminder of our shared intellectual heritage, a testament to a universal language of logic written into our very nature. If this exploration of ancient minds has captivated you, we would love to hear your thoughts in the comments below. And subscribe for more journeys into the deep mysteries of our past.